This is one of those glamour shots. Actually, the next three pictures are kind of glamour shots, just to get a really up close and personal view of a power cable. So this water tree we saw is growing from this black shield that goes around right there, back in this previous photograph. So you get to see all the pieces, and then we also cut this out so that it's in the shape of the Novinium logo, which is kind of cool. In the real world, you wouldn't cut it like that. Another glamour shot of fluid. This is actually water. It's supposed to be, it's red dyed water or orange dyed water, and interest in the illumination. And then we have, again, a URD cable, so it's the combination of chemistry and the power cables all in one place. That's what the beaker's for. And then this picture, I was trying to create a glamour shot, and the way I did it was I put our light pipes, which you can, it looks like these purple laser beams coming in from the side, but those are really black pipes, and the light's coming through those pipes, and it's just pumping the light into the polymer, and then the whole thing glows. And of course, we're in a black, dark room, so the only light is coming from the cable itself. Just kind of a cool shot. So this is the outside of an injection adapter. It stops right there, and then the big hunk of aluminum in the middle is the connector, and then there's another injection adapter that goes the other way over there. But just focusing on one injection adapter, you can see that we have sealing mechanisms, little teeth, and an O-ring right there that stop the fluid from leaking out, because we're injecting the fluid into this annular space right here. So you don't want the fluid to leak that way, you don't want the fluid to leak this way. So here you see another O-ring and some more teeth. But this is a key feature of, and there's 2 or 3 patents on this piece right here, is that it's a trapezoid. So when I have this polymer and I squeeze this down, the polymer cold flows into that trapezoidal shape. And if I didn't do that, and we tried not doing that in the beginning, what happens is the polymer has a different coefficient of thermal expansion than the metal does, the aluminum or steel does, and they're quite different in fact. So when the cable heats up, the polymer expands faster. That's not a problem because it's pushing harder against this aluminum, let's say, and so that's not a problem. It's still sealed. But the opposite, when it's cooling down, then the plastic retreats faster than the metal, and it pulls away from that surface. So I had liquid pressure right here. It would want to leak out that interface. So when we tried regular teeth and stuff like that, the fluid would still find its way out. But the trapezoid solved that problem, because as the polymer tries to retreat this way as it's cooling, it pulls these corners up against that, and it makes a seal here and here. So that's, again, like 3 patents on that right there, and that's a key part of our technology. And this one is a bow tie water tree, and it's in the middle of the installation, and again, there's some contaminant. I've seen insect wings and things like that. So in the olden days when they made cable, they weren't particularly careful at how they put the polymer in, and they extruded it out, and insects and pieces of tools and so forth were getting mixed in and causing these kinds of problems. Today, if you go in the same factories, they have the guys have hair nets on to keep their hair, and eyelashes and everything is all protected. It's like a clean room, because these kind of contaminants are bad, obviously. Is a picture of another water tree, actually at least 2 water trees here, and this one's undyed. So those are big enough water trees that you can see with the naked eye, which you usually can't. So it's a pretty cool picture, and I think we have one more of these upstairs too, a different shot. The other feature here is this area right here. This is called a halo. And a halo is a high concentration of water that's caused by the thermal cycling of the cable. So even without voltage, you get a halo formation just from temperature fluctuations. But the water tree is really the fundamental cause of degradation of the polymer. The last ones are growing from the inside out, and these ones are growing from the outside in. And they do from both. On smaller cables, like the previous picture, they typically grow from the inside out, because the electrical stress is higher in the inside just from the geometry. But on feeder cables, there's more water on the outside, so they typically grow from the outside in on large diameter cables. But they can be both, either. Those candid shots of a Novinium employee having fun. And that's Dennis McDougall, and he's just always happy actually, but he loves his job, and he's using a time domain reflectometer or radar to test whether there's any splices or neutral corrosion in the cable that's underneath down here in this vault. A connector cutoff tool. So I think Norm did most of the design work on this, and if you look at these blades and you have this connector, a lot of times when the cable comes out of the ground, there's no slack in the cable at all. And it comes up and it lands, and it's supposed to plug into a certain point on the equipment. If you cut off just 1 inch of cable, you wouldn't be able to get it back into place. So we have to be very careful. We cut off the connector without cutting the cable, and then this tool cuts into like that, and it falls off very easy, and you lose no conductor at all. So you don't even lose a 1/2 inch of conductor. So this is not a commercially available tool, so we had to make it ourselves, and we occasionally sell them. Norm, what do we sell them for?
About $8,000 to $10,000.
$8,000 to $10,000 a pop for what looks to be a fairly simple thing, but hey, we deserve the profit. And then looking over here in this other office, you can see just a bunch of different sizes and shapes of these injection adapters that, again, are our bread and butter for sustained pressure rejuvenation. And they come from the little tiny ones for 1/0 cables to Norm's got one that big for transmission class cables. Here's our first upstairs picture, and it's another candid shot. Marco's not smiling, but I can tell he's having fun. I remember taking this picture. It was at Florida Power, or it says SPR injection. Yeah, it was at Florida Power and Light, and it was one of our earliest injections in the first year when we started in like 2006. And yeah, he's having fun there. Now here's an interesting picture. This is a failed cable, and you can see the actual hole that was blasted through the cable in the photograph. But you can also see the water tree behind it. Very often in like the previous failures I showed you, the hole is so big that it destroys all the evidence of what caused the failure. So it's unusual to actually get a picture like this because you have the failure and you have the cause in the same picture. Again, usually that evidence is erased from the failure itself. Artsy shot, purposely blurred a little bit just to make it a little softer. So I use that picture for some marketing type stuff. But it's a different cable than the one we saw before, but cut in the same way to have that Novinium logo built into it. So in this photograph, an engineer is meticulously removing this white and black powder off the strands of this aluminum cable. And it's a very challenging task because each one of these strands has to be individually splayed out into this arrangement, and then you have to use sandpaper, or in this case a sort of a wire brush, to get all of that stuff off. Because aluminum oxides, and most of it's aluminum hydroxide, is non-conductive, and it coats the surface of these aluminum conductive copper strands. And then when you go to crimp onto this or swage onto it, the electricity has to go from the innermost strands through the outermost strands into the aluminum barrel and then get transmitted further down. So anytime you put an insulator between those layers, it's harder for that electricity to do that. And what electricity does when it struggles against resistance, it creates heat. So it gets hotter and hotter, and as the heat goes up, the resistivity goes up as well. It's called thermal runaway, and it'll actually cause it to fail. So we found that this effort, while very painstaking, is absolute requirement in order to get these to work properly. And we lead the industry and explain why that's the case. We presented papers and stuff, and we're very meticulous in that. We have a really great record of not having those fail in thermal runaway in the actual real world. We'll interrupt Dave Lewis for a moment. Are you still running there? Mm-hmm. For Dave Lewis for a moment to look at this photograph, which has lots and lots of water trees in them, and they're all growing from the outside in. And again, you can see that in this case you have a really large conductor, and so the stresses between the inside and the outside are pretty much the same. And as I mentioned, you have the water source on the outside, so the majority of water trees often grow from the outside in. This is not an unusual picture in the sense of the number of water trees that are present. When an independent laboratory does analysis, they'll count your water trees for you if you pay them $1,000 or something. And what they do is they slice the cable up into a bunch of slices, and they report that number in water trees per cubic inch of insulation. And it's typically in the hundreds or even thousands of water trees per cubic inch. So of course a cubic inch of insulation is just that big, a little small thing. So that's a normal amount of water trees. This is a bit of a glamour shot. It's a submarine cable. It goes out to Anderson Island here in the Puget Sound area. And the guys that install these cables, they try to bury them underneath the ground until they get past the low tide point, because you don't want people walking down the beach and playing with them or anything like that. Well, the tides, God has another plan, because the tides and the waves move the stuff around. So here the cable is exposed. As you can see, it's buried again up here, and it buries again, but they get periodically exposed. The outside black layer is steel armor wires that are designed so that, yeah, they can take rock hits and anchor hits from small boats and stuff like that. But you'll often see, if you ever boat, that you'll see the signs on the shore that say, underwater cable here, don't drop your anchor and don't pull nets or something like that. Because if you snag that with an anchor or a big net, if you're a trawler, you can break the cable and cause a serious outage. A Novinium contest for finding and taking a picture of the best decorated transformer that you find. Right now, Glenbertini is the leader in that competition with this photograph right here, which is in Spanaway, Washington, for Tacoma Power. And at this trailer park, they didn't like having that transformer in their front yard, and so they swift it up very nicely there, and something that anybody would be proud to have in their front yard. Safety is really important at Novinium, so we have our safety equipment, our personal protective equipment in that photograph. And here is yet another glamour shot. You might notice a couple of things different about this cable than the previous ones we saw. We have a copper conductor, which is very typical in industrial settings and also in metropolitan downtown areas. And you might notice the neutrals are a little bit smaller too. That's very normal for feeder cables. Then there's this mylar wrapping, and then a jacket. So this is a jacketed feeder cable because it's got lots and lots of strands. Looks like I'd say 61 strands there. So it's a lot of strands in that bundle. Here's one of two pictures of Norm in the tour. You can pan to Norm if you want there. So this was Ketron Island, a small island. I think it has 11 homes on it or something like that. And it's Tacoma Power, and they don't want to replace that cable because it would be millions of dollars, or at least $1 million to replace it. And I think we treated it for $75,000 or something in that neighborhood. This is one of Norm was fairly new on the job at that time, so he was curious about everything. So I actually want to ask you now, Norm, what is it that you're looking at so closely in that tube?
We didn't have any flow meters, and so I can see a particle move about 15 inches in say so many seconds. So I knew it was one cc, depending on how fast the particle moved. So I was trying to see if it was moving or not.
Mystery solved. No. I took the picture. I didn't know what he was doing at the time. It's a great picture. Thank you. And swinging on to the other wall, all the cables that we've looked at so far are all primary cables. So primary means a voltage typically several thousand volts to 25,000 volts. This is the kind of cable that might run to your house from the transformer, the decorated transformer that we saw before. They're called secondary cables. And it carries 110, 220, or 440 volts typically. And in this case, the aluminum conductors, we can just see just a little piece of here, have oxidized and hydroxylized, which is aluminum hydroxide, and it's completely gone. And so this cable failed catastrophically, and we have a new product to be able to deal with that problem as well. So one of the things that is sort of maybe unfortunate, but or fortunate depending on your perspective, that we have to deal with are splices. And so this is just a picture, a kind of a close-up picture, as glamorous as you can get of a splice that's come out of the ground, so it's nice and dirty. And splices are installed when a cable fails. Sometimes splices are installed when they just run out of a reel of cable and they're just going to start a new reel. So they're periodically in the ground. Typically, half of the cables that we encounter, or maybe a little bit less than that, 30 or 40%, have splices in them when we show up. So we either can flow through those in some cases, or we like to replace them actually, because they're sometimes 25, 30-year-old splices, and they could be potential failure points as well. So excavating to get to those splices, I'll show you a picture a little bit later of what that looks like, is a pain in the butt. That's the bad news. The good news is that replacing those and dealing with those improves the reliability of the circuit, so it's a good thing to do. It's just a little bit of a pain in the butt. Swinging around into Stephanie's office here. This is one of the things that we'll do down here in the laboratory is we take a hunk of cable and we put it in hot silicone oil, and it gets hot enough that the insulation, which you've seen pictures of, which is normally opaque or semi-translucent, becomes transparent. And so you can start looking for specific defects, like if there was, let's say, my wing of an insect or something, you might see that in here. Well, this is a failure hole. There's no particular defect to be observed in this one, but you can see how the failure looks a bit like a wormhole, going through the insulation. And so here we have a bunch of things happening in this one. We have our water tree again. This time it's growing from an imperfection that was created by neutral corrosion problem that's kind of outside the picture here. But we have this huge water tree, and then we have this electrical tree. So the water tree is what is the fundamental cause of insulation degradation in polymers, but the electrical tree is what happens just before it fails. So this cable failed 5 inches away from here, and it blew a hole through like the ones that we've seen. But this started to fail here too, but the other one failed faster. So the electrical tree, unlike the water tree, is an actual channel. If we got up closer with an electron microscope, you'd see a worm-like channel through there, and that's from lightning bolts. Small lightning bolts called partial discharges going off inside there, and then each time a lightning bolt hits the end, it melts or decomposes the insulation at the end, and it grows longer and longer. So these electrical trees, once they start to form like that, they propagate through the insulation in minutes or at most a couple of days. So it's a very, very fast process. We have, this is what splices look like in the real world. And yeah, mud and dirt. And so our guys have to go dig the hole, not damage the cable while they're digging the hole. They usually use a backhoe to get close, and then they hand dig to get to the last 6 inches or so. And then they have to put a new splice in without getting dirt in it. So in this mud pit. So they'll lay out paper towels and various things in order to do that, but it has to be really clean implementation. So here's 2 water trees, one growing from the outside in and one growing from the inside out. And again, this one is native in the sense that it doesn't have any dye. So this one's giant, covers about 90% of the width of the insulation, so that's a big tree. This is the a cross section of the Anderson Island submarine cable. We talked about the steel wires that are protecting the inner piece from anchor hits and stuff like that. And then we have jute, which is a plant fiber that just is packed around it. And then you have 3 cables that are obviously copper strands. And the pink insulation is EPR insulation. But what's interesting here is that if you look really carefully, there's no neutrals, but instead there's a neutral foil. And the neutral foil should go all the way around, but it doesn't. In each case, if you look, it goes to there and to here. So after this cable failed, it turned out that the reason the cable failed was a failure of the neutrals as opposed to the insulation. And there's a long story associated with that too, but the short version of it is that after we got through and started doing some analysis, we found out that in the subsea that there's a bacteria that really likes to make acetic acid in an anaerobic, non-oxygen environment. So guess what you get when you go into the mud underneath the ocean? It's an anaerobic environment. And so you get these bacteria feeding on stuff that's there and making acetic acid, and acetic acid dissolves copper. So all the copper neutrals are dissolved by basically these bacteria. And that's something that we didn't previously anticipate. Really bad idea to let thin copper foil come in contact with seawater. This is my goth glamour shot of a cable. It's actually a color photograph, but everything is black, white, or silver. So it's kind of artsy. Not everybody gets it. If you don't get it, don't feel bad. So this is a hunk of plastic, clear plastic. And we created this as a little statue to demonstrate how partial discharges work and to hand out to our best customers. And so let me describe how this is made though. So we go to a particle accelerator in, I think, Chicago, and you have these plastic pieces cut out in advance. And then there's a metal piece that goes on top of the plastic piece, and it has sort of trapezoids cut out of the metal. So there's 3 trapezoids, and then you put it into this particle accelerator and you hit it with beta radiation, which is electrons at close to the speed of light. And so the electrons actually penetrate into the plastic because they're going so fast, and they get distributed where the metal's not blocking it. Then you take those and you, with gloves on, with hot gloves on, you take those and you move those onto a dielectric surface, and then you have a probe that's grounded, and you touch the probe to that point right there, and all that space charge instantly discharges, and it's instantaneous. This tree structure, this fractal tree structure is formed. So we create that. That's how we create them. Then we mount them, and I think I don't know if we have. Yeah, I think we have another picture of one of those. This is Tony out in the back, and he probably never thought he'd be part of a glamour shot before, but this is a glamour shot that we used on our website. I don't know if do we still use that one? Mm-hmm. We still use that shot, and again, it's that, I think it's the same cable we saw before, perhaps, and yeah, it's just a nice picture of a person and a cable. So that's basically the same device that we saw before, but now we've mounted it with some copper conductors and some faux conductor shields and some lighting to get the final effect. This is glamour shot, maybe only in my mind because I've been in this business for 25 years, but painstakingly shot to get it the paper white background, and interesting because you've got all the play of colors. Interesting to me as a chemist, chemical engineer. I find interesting the different oxides on here, which I'll explain in just a second in the next picture. But that's a very typical cable that we would see in the field, just cleaned up for photographic purposes. That cable that we were just looking at this is the same picture, but now up close and personal with a microscopic view. And now you can see the different oxides on the copper surface, and there are 3 of them. Copper oxide is the black color. Copper hydroxide is the white color, and then there's some copper carbonates and copper sulfates as well that give it the bluish and the green colors. So all of them are represented. All the different possible oxides of copper are on that one photograph there. So remember before we saw one failure. Here's a failure with an even bigger hole. Again, we have the melted copper. This one's I call this one the black hole because you look inside and you see nothing. So it's just, again, an interesting picture of a fault. And as you can imagine, you cannot find out what the cause of that fault was because whatever it was is destroyed in the explosion that occurred. By the way, when a cable faults, I told you the temperature before, but it's typically 20,000 amperes of electricity. So that's just a whole lot of energy released really fast. And then here's another water tree, another shape. So they come in all sorts of shapes and sizes. Some people want to call them bush trees and stuff like that. But the last thing I want to say about water trees is when I was explaining the electrical tree, I was clear that there was a channel, but I wasn't too clear what a water tree is. It's a chemical oxidative degradation of the polymer. So there's no channels. No matter how close I look at that with a microscope, I'll never see any physical things until I get down to the molecular level where it's oxidized polymer is what is there. Here's the other Norm picture, and I'm tempted to let Norm tell the story, but I bet you my version will be more fun, so I'm going to go with mine. So Ketron Island again, maybe that same day that other picture was from, or around then, because I think we were out there almost every day. The problem with Ketron Island, from an operational perspective, was the ferry only went there twice a day, and the ferry only lingered on the island for 15 minutes. So if you went out on the ferry and you thought you're going to run over and do your work, if you could do it in 7 minutes or so, then you could get back to the ferry in time to go back. Otherwise, you're there until 4 in the afternoon or something like that. So you either had to spend the whole day there or 7 minutes. Those were your choices. So neither one of those was particularly attractive to us. So we christened the SS Novinium, which was my kid's canoe. And we would go out there almost daily. We had to sort of illegally cross the Burlington Northern Railroad tracks in order to get to this riprap seawall, which you can't see on the left side of the picture here. Go down the seawall, and then we launched the boat. So we were safety conscious. We made sure we had our marine safety gear on, and we were carrying expensive equipment with us as well. So we carefully took those expensive pieces of equipment, we wrapped them in life preservers. so that if the thing would tip over, that we would be able to recover the expensive equipment. There was one piece of equipment, though, that Norm is holding in his right hand there, which you just see the top of it. That's a nitrogen bottle about this big, and it's steel, and it's filled with nitrogen. And Norm told me that we needed to put a life preserver on it because it would sink. And I said, no, it's full of air. Ships are made out of steel, and they'll float. So we don't need to put a life preserver on that one. So lo and behold, 2 or 3 minutes later, as we get ready to leave, Norm reaches across out of the boat to the riprap seawall to push off, and not knowing apparently that you can't really lean off of a canoe. And so he tipped us into the water. Now, some people might think that Norm doesn't know how to go in a canoe. That would be one conclusion. The truth of the matter is that Norm wanted to prove that I was wrong, that thing would sink and not float. And he was right and I was wrong, and he succeeded in that. That's why he's got the smirk on his face there.
Congratulations.
Got him all that.
Oh, this is a cable from Australia, one of the first cables that I got. We had a customer, our very first customer was in fact in Australia. And I just put some, I think, baby oil or something on it to try to make it attractive, and took a picture out my driveway, and that's the first glamour shot of an Australian cable that we took. So we started almost the tour on these injection adapters. There's quite a few pictures of these injection adapters. And so here we have an injection adapter. And it's just a part of the bread and butter of Novinium technology-wise. And so then this tool is the tool that installs that injection adapter. And it's also bread and butter for us. And so it's a 45-ton tool that just squeezes the heck out of that connector. And it squeezes it circumferentially down. They call it a radial swage, but I like the word circumferential better because it puts the same force along the entire outside of that circumference and makes it circular when it's done. So that's a key part of making that seal be very effective. So we own a lot of those swaging tools that aren't typically used in the small cable environment. They're typically used in the big stuff in substations. So but it's a special application for us. So that picture shows the swage kind of happening. And this picture shows a cutaway. We took out one of the dies, so you just see half. And so it just shows you how it all lines up. The gentleman's fingers are down here holding on to the cable, and there's a special tool stop because you got to get this position in exactly the right spot. So everything's lined up perfectly, and of course the other half has to be in there, and then the swage occurs. And this piece of metal right here will be squeezed down, and it'll be the same diameter as this when it's through. This one is stainless steel, so it's a lot of force, 45 tons of force to make that squeeze happen.
That IA is really one of the key technological innovations there, and we continue to innovate around that. Where do you see that going?
Gee, I think it's, other than cost savings, and it's never failed. IA seal has never failed when it's properly installed. So it's a very robust technology that probably won't go very far, other than bigger sizes, other sizes, and we've switched from stainless steel to aluminum largely and things like that.
I think there's 35 different sizes now.
35, and there's going to be more.
Yeah.
Because the new sizes always are coming along.